Okay, let's talk about stacks. We're still in memory management, okay? And we're still building on an example um, of a memory manager that we're building in Java. And again, just to reiterate, nobody in their right mind is ever going to build a memory manager in Java, okay? Um, just using Java as a vehicle for expressing really kind of algorithmically what you would do. This thing is actually going to be, built somehow and available when the program is running, dynamically, whether there's an interpreter or a system kind of running at the same time, or if this is stuff that is, kind of assembled and built into a program so that the program has its own stuff, or whatever the mechanism is. These features have to be there, okay? And so Java, I just hope you realize, don't get too wrapped up over, wow, people build memory managers in Java. No, not really, but we've got to show it in something, and it's really as good as anything. And in terms of how the book is flowing, we're using Java, at this stage of the game, so it works. So, just again to reiterate that, in particular activation records, and not just activation records, right? But we're going to talk about activation records as an example of when a stack shows up and becomes an important thing. Now, the truth is you can talk about activation records, you can talk about, the way, obviously the way function calls get made, which can be viewed either directly as an activation record or as some other kind of hybrid, where you push things on the stack as you're making function calls, in a very simplistic kind of a system, right, without a lot of elaborate management of activation records. And there's also, just anyway, this is a really good example of when a stack is the right data structure to use. It's not the only environment in which you would use a stack, but it's a good example of one, and so it's fine for our purposes. Okay. For most languages, we're fine if I can, I need an activation record, meaning that I've entered some new scope. I've entered a function, I've entered a block, I've entered some chunk of something, where there's a scope and I need to hang on to that, that thing. Um, and I want to basically take, this activation record and allocate it when I make that call, for example, a call into a function. And then I want to deallocate it when I'm coming back out. And I'm ignoring all the complexities of activation records that we talked about. But in that kind of a simplistic model, a stack is a perfect data structure to use to hang on to that kind of thing, okay? And it also just kind of gives us an illustration of this notion of using a stack for this kind of a memory management in a programming languages context. So here is our arbitrary stack, okay? Let me give you a few things about this stack just to kind of help you get your head around it. So first of all, yeah, really, Dr. K, this is an 8-word stack? Yes, my friends, it is an 8-word stack. So no, is that a realistic stack, in any kind of real system? No, no, it's not. We're just doing it because it doesn't matter if it's 8, 80, or 80,000, the principles are the same. So we're using 8 to keep it simple. Um, the stack is going to start here at the top and it's going to grow down. And, just again, understand that addressing can be viewed as from the bottom up or from the top down. Stacks can be viewed as growing from the top down or from the bottom up. There's a lot of different ways of, well, there's not a lot of different ways, but every possible way basically, can and has been used to deal with using memory locations as, using them as stacks. Okay, so in this case, the illustration that the author of the book has chosen to use is one in which the stack grows down from high addresses to lower addresses. So it does make checking at the bottom, right? I mean, you basically know, depending upon where the stack pointer's at, you know how much space is left automatically, right? I mean, if the top says 8 right there, you've got 8 words left. If the top gets to 1 and you make a request, and you know immediately how much is left, and that's super convenient. And then I can go like, oh, I need 3 words, and you can go, hey, top equals 1. So okay, guess what that's called? Stack overflow. So, you know, that's it. It's not just a handy website. It's actually a thing. And anyway, I mean, you can do this kind of any way you want, okay? The other thing to recognize is that top, you know, sometimes, so top is a fine way to refer to that. I've seen it referred to, you know, as a stack pointer, something that basically shows you, you know, kind of like where the next thing is going to go. If I push onto the stack, it's got to go here in location 7, okay? It can't go up here because the top is 8, so I'm going to push here. You know, again, different ways of managing the stack pointer, right? I can point at the next spot where stuff needs to go, or I can point to the top of where stuff actually is. You know, pretty much one of those two options. But again, there's a lot of ways of implementing that. But that's kind of our data structure, okay, for the stack. And then what we're going to imagine to sort of have this make some sense. So number one, this m dot push, okay? I mean, the author talks about this in the book, so it's not really here clear in the slides at all, just looking at it. But what we're actually doing is that we are assuming that we have that stack manager, the one that we started building, and that the stack manager has been allocated as an object, and that the variable that is that object is m, okay? So that's why m. Push is one of the methods inside that memory manager, okay? That stack manager. Push is one of the methods. We're going to get to it, but it's okay. You understand from a data structures perspective what a push is and what a pop is. So just imagine that I can take the stack. I'm making a call. The program makes a call to the stack manager, and it basically says, "You stack manager, the manager of this stack. This data structure is the memory inside that stack, referenced by m." He's got a method called push, and I say that I need three words. Okay. So he's going to basically go, because I'm in this mythical world, my activation record occupies 3 words. So I'm going to basically grab words 7, 6, and 5. I'm going to put my first activation record into that spot. And then when I make that call, I'm going to set the top value, okay, which used to be 8. I'm going to push that value 8 right into that location. And then I'm going to reset this value to be 4. So the top now will point to this location 4. And at location 4 is the number 8. Now, why am I doing that? It's because later on when I start popping back off the stack, I need to know, you know, how much to pop back off. So I'm going to pop back to location 8 when I get to this point. When I'm here and I'm popping, I've got to pop back to 8. Okay, so this comes in as one contiguous chunk, all right? And then the other part that's sort of, you know, not super mysterious, but when I make this call to m.push with a parameter of 3, saying I need 3 words, it returns the value 5, okay? And 5 is the address of the activation record. And this is the part where you just got to hang with me. I don't know if I like it conceptually, because it's just a little harder to view. If you don't already know this, it's a little confusing, because I start here with a stack pointer at 8, right? I grab 3 words, fine. And then you'd think, since the stack's growing this way, that what's my first word of that activation record? You would think it was 7 because I'm growing this way. No, I'm grabbing 3 words, and then my first spot is 5. So it's almost like, I don't know, there's probably a different picture I would draw, but you're like jumping past 3, and then but the direction's the opposite direction. So 5's actually the first. Okay, so I'm really sorry that that's sort of pedagogically a little bit clunky, but I hope you can get the idea. Stack pointer's at 8. I shove the 8 here. I move the 4. I put 4 here, which means my stack pointer now points me to here. I get 3 words for the activation record, and the address of that activation record is 5. And then it's going to go that way, kind of up. So stack grows down, but memory still goes that way. Anyway, just so you understand, so you don't feel too bad. You know, I've seen this stuff, you know, in a lot of different settings, And this is, I don't know, for me anyway, right this moment, it feels a little clunky and hard to kind of, honestly, hard to teach it because it's a little unfair to you. Okay, I get that. But try to get your head around that. Then the program, you know, somebody calls, it calls a function, right? And when the program calls a function, down underneath, the program is going to call also to the stack manager another push for 2 words for the second activation record. And again, the 2 and the second don't matter. That's just coincidental. It just so happens that this call needs an activation record of 2 words. There's nothing magic about 2. And then again, I'm also not liking this. Second 2 returns 2, and then there's the first of the 2 words. And I just, it's too many 2s, and they're not the same 2. Okay. I decide that my activation record is 2 words. That's why that says 2. I'm going to return the value 2 because that's the address in memory when I'm done. And again, I go, the words in memory for the second activation record are 2 and 3 in that order. So kind of think of it going up. Okay. And it just happens to be the second activation record because I did one already. I made a function call and that got me to the next one. All right. Then, of course, what I'm going to do is I'm going to take the prior stack pointer, which was 4, and shove that into this spot. And then I'm going to reset the stack pointer, which is being called top here, and set that guy to 1. There we go. Now, the other thing to kind of say here is that the stack is basically full. I mean, we can't even, as far as activation records are concerned, we could use that stack. If this is just a stack that we use to store activation records, then it's full. If it's a stack that we use for other stuff, then it's not necessarily full, but I do only have 1 word left. You blow past that, there's going to be an overflow. Okay, now we get into the actual implementation in Java. This is not crazy. It's a bunch of code. Here, watch real quick. 1, 2, 3 slides of code. Just walk through this. If you're not a Java guy, you don't know really much about Java, don't worry about it. We're going to walk through it right now and kind of make some sense out of it. So this we already saw before. It's a stack manager is the class, and we've got the memory, right, which is the memory we are managing. It's a pointer, right? And then we've got top, which is the index of the top stack block, what I call a stack pointer. And then we've got the constructor. This is all we've seen. We added top, okay, because we need that stack pointer. And we had already in the constructor, when we initialized that memory, right, we had that point to the memory we were given by the operating system, which just, we're calling initial memory. Now what I do is I have this top that I declared, and I'm going to initialize him to be memory.length, okay? Now, if you go back again, right, top is memory.length. Again, now top is going to be, at the very beginning, I'm backing up right there. We were given a length of 8. So top is 8, which means it points to there just it's actually outside the stack, but it says there. So I start to move, immediately after that. I hope that makes sense. So if I'm given the size of the memory allocated, I also have the initial value, where am I? Right there. The initial value for top, or AKA stack pointer, okay? Then what I'm going to do, I'm going to give you push, and then we're going to give you pop, okay? And then on push, just a pointer already to this idea. We're going to introduce throw here, and we're not going to really go deep on that, and we're not even going to talk about it until chapter 17. So we haven't gotten to it. If you don't know what it is, essentially it's exception handling, for when we get that stack overflow error, okay? And then again, as you can see here in the comments, these are Java comments. We're going to allocate a block and we're going to return its address. And something to think about, right? I'm grabbing this memory from a stack. Do I care at this point whether that memory is on a stack or pulled out of some heap or just, somewhere random? No, I don't really, do I? And so the address in memory that happens to be, allocated to that stack is just an address in memory. So the notion that there's a stack, it's not like there's a separate box over there, called the stack. The stack is just like a region. It's like I went out to my front yard and I grabbed some of that cool spray paint that you can do to paint where the power lines are underneath your grass. and I just said, this grass here is my stack. It doesn't matter. It's all grass, but I'm just saying these are going to be my stack. Does that make sense? That's all we're doing here. And so it just happens to be inside the stack. And by the way the thing sets up, we've got this, top of the stack. So what do? I got a parameter, which is request size, which is the size of the block that I need to allocate from the stack. Okay, it's got to be greater than 0, one or bigger. I've got a return value right there, the public int. That is going to be the block address. Okay, so that the caller knows where that is. And then we're going to throw the Stack Overflow error if we're out of stack space. So here's the code. I take top. Now you're like, where's top? Okay, if you're not a Java programmer, even if you've done any object-oriented programming at all, you know that if we go back, that top is allocated here. Is actually allocated right up here is where he's declared, and then he's kind of given a value during the constructor. But he's part of the memory, the private data of the Stack Manager object. Okay, he's declared up there. So all of the methods inside of the Stack Manager object can see that variable called top. Okay, because it's private, they can see it inside the object. I take that value, I save it away as old top. I'm just hanging on to it for a second. Okay, and then what I'm going to do is I am going to take top, which is the stack pointer, and I'm going to decrement it by the requested size plus 1. So they said I need three words for an activation record. I'm going to grab 4. Why? Because if you remember, I'm going to grab the activation record space, and I'm going to grab one more to hang on to the old top, aka the old stack pointer, so that when I get to there and I'm popping, I know how far back to go. Okay, when I'm popping. Let me see. I then check to see if the top is less than 0, right? Then the result of that top was I went too far. I ran out of space. So that's when I do this. I do a new on Stack Overflow error, which creates that object. And then the throw, again, we're not going to get deeply into it, but just understand that it's exception handling. Okay, allows the system to do what it should do when we get a Stack Overflow error. Then I take memory pointed to by top, right, which is where, again, you're like, where's memory? Where's memory? Okay, memory is right there. It's right there. That's where it was declared. It's a private array that's inside that object. Now here in the push, I can go to that memory at the location of top. That, by the way, is the new top. Okay, and at that location, I stick the old value of top. And again, that is right there. That's this action right there. It's this action right there. Where am I? Right here. And then the value I return is top plus 1. Again, in this case, top is here. The value I return is top plus 1. That's top. So plus 1 is this way, going up. That's 5. That's the memory address of the first activation record. Now, again, it's one of those funny things where when you look at all that, I don't know, it just feels like misdirection, right? I'm going down, then I'm going up, and then some of it's going down and some of it's going up. You got to take a little bit of time and make sure that this is making sense to you, okay? It's there and it really does make sense and it works, but you've got to still, take some time and make sure you get it. Then I've got pop. This is the last function, last method that I'm going to talk about here for this section on stacks, which is when I'm coming back the other way, right? And I'm gonna pop the top stack frame, and this only works if the stack's not empty. And all I'm doing, check it out, crazy simple. I go into memory, right? That array. I look at top. I grab that value from there and I put it into top. Let's go back. So here's what I'm doing right here. I'm at top. That's location 1. At that location is the value 4. I grab that 4 and I put it, boom, right there. And as soon as that's done, I'm here. And you're like, wait, but what about what about that? Sorry, what about that stuff right here, the second activation record? Well, the truth is, it's still there. It's just sitting there. But My stack pointer changed, so I ignore it. If I were to just go back and look, it would still be there. But I'm not going to go do that because I'm now pointing here. If I pop again, boom. Okay? So that's pushing and popping from a stack, and in particular, managing activation records on a stack. All right, so on the next podcast, we're going to talk about heaps, which is another, kind of data structure that gets used for doing certain kinds of memory management and memory allocation in a dynamic system in programming languages.